Hello. Can you hear me?
Good evening, Professor Kotagiri. I think we'll start probably within 14 minutes.
Okay.
Yes, because the IST is as of now 2:46. So we are
Okay.
starting shortly, sir. Please stay in the
Sure,
meeting.
no problem. Is the video is okay?
Absolutely fine.
Okay. All right. I'm just going through my slides to make my mind tuned for the talk. Okay.
Yes, sir. A very good afternoon to one and all. On behalf of the organizing committee, I'm welcoming all our dignitaries, our eminent speaker for the day, and participants on the final day of the faculty development program on research trends and methodologies in machine learning, RTMML 2022, organized by the Department of CAC, CAC Artificial Intelligence and Machine Learning, CAC Data Science, CAC Cyber Security in association with IQAC of Haldia Institute of Technology. The journey started from the discussion on machine learning all the way to deep learning, multimodal summarization, computer vision, and pattern recognition, along with research ethics. And we are in the final session of this FDP. All these participants are requested to follow the session on respective platforms watchfully. You can put up your query or questions for our eminent speaker for the day on chat box. In the end, we will definitely have the Q&A session along with the valedictory session. Both attendance form and online test form link will be posted at the very end of the session in chat box of Google Meet as well as YouTube streaming meeting link also. Form link will not be posted over WhatsApp. Examination form will be live for around 30 minutes from the time of its posting. So in this regard, participants are requested to stay attentive and submit both the forms within 30 minutes from its post. We are privileged, fortunate, and honored to have Professor Dr. Ramamohanarao Kotagiri with us today as our eminent speaker for the day. Professor Rao have received PhD from Monash University, Australia in 1980. He was awarded Alexander von Humboldt Fellowship in 1983. He was at the University of Melbourne during 1980 till 2020 and was appointed as a professor in computer science in 1989. Professor Rao held several senior positions, including Head of Computer Science and Software Engineering, Head of the School of Electrical Engineering and Computer Science at the University of Melbourne, Associate Dean of Research as well as Deputy Dean of Faculty of Engineering and Research Director for the Cooperative Research Center for Intelligent Decision Systems. He has served on the editorial boards of the Computer Journal, Universal Computer Science, Data Mining, IEEE TKDE, VLDB Journal. He was the program co-chair for VLDB, PAKDD, DASFAA, DOOD conferences. He was also a steering committee member of IEEE ICDM, PAKDD, DASFAA, and ICDE. He received Distinguished Contribution and Service Award by ICDM, PAKDD, and DASFAA. Professor Rao is a Fellow of the Institute of Engineers, Australia, a Fellow of Australian Academy of Technological Sciences and Engineering, and a Fellow of Australian Academy of Science as well. He was awarded the Distinguished Contribution Award in 2009 by the Computing Research and Education Association of Australia. 85 PhD students have graduated under his supervision. So we are extremely sure that all the participants will find today's session to be very much informative, which will help in the research and definitely gaining further knowledge. So without any further ado, I'm inviting Sir to deliver his talk on the topic of artificial intelligence equals to big data analytics plus machine learning plus cloud computing plus domain knowledge. Welcome, sir, and over to you.
Thank you for your kind introduction. So do I have an hour and some time just for presentation followed by Q&A?
Yes, yes, definitely,
Okay.
definitely, sir.
So I should be able to share my slides now, right?
Yes.
Okay. Okay, I need to give permission. Okay. Can you see my screen?
Till now, we are not getting that feed.
Okay. Let me try again.
So there's a share now button or present now upward arrow, and you can share your entire screen.
Upward arrow. I don't see anywhere.
It is down below.
I
There is a
shared your entire screen. I
yes,
said
yes.
that. I shared. Okay. Yeah. So I allowed it to do.
Hello, am I audible, sir?
Yeah, I'm trying to share slides, and
Sir,
the error has come now. Entire screen.
Yes, you can click on that, the present button.
See, 1 minute. I said share it, but it's not coming.
sir, your entire screen.
Yeah, I did that. I'm trying again. The up arrow.
Upward
entire
arrow,
screen.
your entire screen. Then whatever miniature version of the full screen coming, you need to select that, and then the share button gets enabled.
I don't see my other screens.
A
I
small.
only see the Google Meet. Okay, let's see. I can only see one screen. So any luck now? No.
Sir, can you get the present now up arrow in the below of your screen?
Yeah, I did.
You click on that and then your entire screen.
Yes.
I said
Your entire
your entire screen.
yes,
Yes.
sir. Click on that.
Yeah, I did that.
And
Share. Okay.
Another window opens up after that.
System. So it's saying can't share your screen. Google Chrome might not have screen recording permission on your computer, which I kind of allowed it. Open system preferences. So maybe I should try from my Firefox. That'd be better.
Yeah.
Let me try from Firefox whether it works. Okay.
Yes, sir. Okay.
No, it's not coming. So should I send my slides to you? Oh no, that's a very big document. So
Yes, sir. Yes, sir. You can send your slide, then we can play it.
Okay, I'll try to send it and see whether it works.
Yes, yes, yes.
It's about 19 megabytes. That's why I'm a bit concerned.
You can share the Google link, your Drive link, Google Drive link. We can download.
Okay. Okay, I'll try do that. I'm sorry, this is always going to happen. So should I share with ML webinar?
Yes, 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 absolutely.
I sent it. Did it work?
Yes, sir, we are checking that. Yes, sir, we got it.
Okay.
Yeah, let me download it. I'm sharing it.
Okay, thank you. Sorry for all you who waiting. Well, we should have tried this a few minutes ago.
Okay, sir, it's all right, no problem.
It's taking too long to download, or?
No, sir, the download is just now complete.
Okay. Okay, perfect.
Yes, sir, you can start.
Okay. Good evening or good afternoon. Here it's for us past 7:30 in the night. Okay, today, first let me thank you for inviting me to give this presentation. What I'm going to do today is that there are lots of technologies that play a huge role in building AI systems. First of all, we need a lot of data, which means big data analytics is needed. And of course, you need to build some models, some machine learning, and you need a lot of computing. Some kind of cloud computing is needed. But in the current AI systems, somehow domain knowledge is not taken into account yet, even though a lot of efforts are taking place, but no easy way of integrating domain knowledge. So my talk basically trying to show that how all of these things can be incorporated into AI models and make them more realistic and also more functional. And next slide, please. Okay, so my talk is basically a bit of motivation and some of the challenges that we face in doing this kind of work, and some of the research issues, some of the breakthrough applications. I mean, these breakthroughs are very small number. There are many, many of them. And the question is that the most important topic that I want to cover is how to integrate domain knowledge into these AI models. And the next question, important question that comes is trust security of AI systems, and how do we make AI systems robust from attacks? So these are the general covering points of my talk. Next slide, please. Okay, so this is a very classic way of how we all do science. First of all, in any science, you observe data. Without data, you don't, even religion is based on some kind of data. So you always collect data, and then that data is somehow processed so that some inferencing can be done. And that we call them some kind of information extraction, and that gives you a knowledge base. And once you have a knowledge base, then you try to use this knowledge maybe to build better gadgets or run the society better way. So whatever the wisdom is somehow outside the scope of basically science. Like, for example, let's say we understand arguments like quantum mechanics completely and general relativity completely. The question is, we can build lots of gadgets, including destructive weapons. The question is, science wouldn't tell you whether you can drop them on somebody or you don't. And this is where we leave this, is a non-scientific one, is the basically wisdom. The question is what we value and how do we run the society. That is not generally scientific. Okay, next one, please. So this is a very important slide to understand. If you look at in this graph, the black curve shows the rate at which we are collecting data. And part of the reason is a lot of social media collection, videos, images, medical data, and scientific data, including all these astronomy with telescopes, satellites, and all the devices we are building, like, for example, the MRI machines, X-ray machines, and all kinds of instruments we build can continuously collect the data. And you can see the number of cameras that are there, probably several hundred billions, and every camera is producing some data in some form. Whether all this data is useful is questionable. And if you actually look at one of the line is the red line, which is basically what we call, from this data, we try to bring some knowledge and wisdom. That seems to be pretty linear. And remember, the scales are, this exponential function we are showing, and therefore, the scales are logarithmic. And you can see that the knowledge is not at all increasing. And the reason is the logarithmic scale, you can't see it. But knowledge is increasing, but minuscule compared to the amount of knowledge we are collecting. Part of the reason we are unable to push this knowledge is that the green arrow is the one that we should be doing in terms of our knowledge and wisdom, and that's not happening, partly because we don't have powerful models to understand this data. And that's what this talk will a little bit allude to. And the question is, how do we get from this red curve to the green curve using the data coming from the black curve? And this is the goal of basically today's AI. Next slide, please. So we know that data collection is very important. We collect census regularly, and we document everything we do. In the research labs, you maintain your lab books, recording everything we do. And you can see, for example, what's happening in the US with January 6th. And everything is completely videoed, and the amount of information and people giving, face-to-face under oath, various kind of things, all of them are completely documented. And you can see this documented information will help us to analyze and come up with some good evidence-based decisions. For example, SARS was controlled so well, partly because the amount of information we were able to collect and understand how the disease progresses. Even COVID, for example, was partly controlled, even though it really done so much harm to society, both in terms of financially and hardship and many deaths. But it could have been worse if we didn't have the proper understanding of collecting this information and understanding how the disease actually, spreads. And similarly, drought. We need to understand, can we predict when the dot's going to happen? And at least now, this seems to be pretty reliable. You know when the flood's going to take place, and we know, for example, El Nino and these kind of effects, we can model them using collected data. And we know, for example, terrorism. We can model impact of CO2, and we can see, for example, natural disasters. How we can apply some of these techniques. For example, can you ever predict earthquakes? Probably we know that earthquakes will happen in some regions more often than any other places, but we cannot really predict them. But however, they do say the second and third episodes of earthquakes can be predicted using AI models much more accurately than some of the mathematically studied prediction models. And similarly, spread of HIV and global warming, salinity, and then, of course, endangered species. All of these things, we can actually model them and understand them by collecting these data sets and inferencing information that is present in those data sets. Next slide, please. And the kind of data we collect is very diverse. So, for example, if you look at astronomy, you will have all kinds of things. You will have images, you have spectrum, and you will have various kind of modalities. There could be radio frequencies, there could be visual, and there could be gravitational waves. All of these things astronomy is collecting. And we can, if you look at the medical images, you will have, for example, you can have MRIs. You can have a video of X-rays, for example. When you're looking at mobility of a person, you can actually see, how a person is moving by their skeletal structures. And we can look at, for example, stock and geology for agriculture, flora and fauna. All of these things, all of them are different kind of things. Some are three-dimensional, some are four-dimensional, that is X, Y, Z, and time. And some are many, many more dimensions in the sense of, if you think colors are dimensions and sizes are dimensions. So basically the dimensions can be many, many, what we can see. And some are sequences, some are relational, some are graphs, and we have to deal with this kind of diversity of the data sources. Next slide, please. So typically, within the computer science, for many, if you can actually divide computer science into basically two kinds of areas. In one area, it is very algorithmic, systematic. That means the models are fully understood. All we need to do is collect the data and actually apply. So, for example, traditional relational database systems like, running companies or whatever it is, or to run a government, you collect the data and you populate them, and then you know exactly how to query them, how to process them. So, for example, you can say a number of births, deaths, or how much money we made this year, how much money lost this year. All of these things are very precise. As long as you collect the data, you can correctly and you can answer them correctly. So this is the main focus of many computer science things, like, for example, how to find the shortest distance between two points in a graph. So all of these things are pretty deterministic algorithms, deterministic in the sense that we do have a procedure how to compute those results. That's what I meant by deterministic. But of course, there also we have a lot of challenges. For example, what happens if you have huge amounts of data? And sometimes the data is not accurate. Some are missing columns, missing rows. Some are wrongly populated data. Some are misvalues, wrong values. Still, some of these things you have to deal with even in this deterministic domain. Whereas in machine learning, we don't have any rules. We don't really understand how a particular system works. So, for example, we can never write an algorithm to recognize, let's say, an image. You cannot write a program to recognize the image of a cat, for example. All we can do is build some kind of a deep a neural net model by showing many images of a cat, and somehow that particular network seems to recognize the cat. And you can kind of explain it how it is doing. It's basically correlations. And if you look at in a typical neural net, you can see that each node is basically doing some correlation. That is an input vector, whatever the input vector you provided, like say, for example, image of a cat, and that is correlated with the weights that we feed to that particular neural node. So it is basically a cosine function in some sense, which is basically a dot product. So what we're doing is we're building many correlated points, and then we're kind of building many such layers of these correlated nodes, and then hoping that somehow these correlations will tell us this is a cat. So this is the kind of algorithms we have right now. But we cannot write exactly how to choose these coefficients except by training models. Whereas a human being, you show a small baby a picture of a cat. You don't have to show this little baby thousands of images of a cat for the baby to recognize next time when she sees an image of a cat, saying that this is a cat. So we still have a huge gap of understanding how to build these models. How you can make these AI models to just see one image and then able to recognize a cat from that. So we are nowhere at that point. So, and again, another question is that how do we incorporate into these AI models domain knowledge? So for example, let's say we know, for example, Newtonian mechanics. Can I somehow add Newtonian mechanics into my deep neural net that is driving a car? So, can I combine these Newtonian mechanics to tell you that how my braking system works, very precisely? We know, for example, the size of the car, the speed at which it is going. I know the road conditions. I should be able to predict how much pressure I should apply on the brakes to stop the car, rather than trying to make this deep neural net to learn all possible situations of, braking conditions, road conditions, and so on. So we don't really know, for example, effectively integrating, let's say, Newtonian mechanics into a deep neural net that somehow helps you to drive your car safely. But of course, there are some efforts that are taking place, and you can see later in my slides that how this knowledge could be incorporated. But still, to me, this is in the very early stages of how we can incorporate this domain knowledge into these deep neural nets. And the next question is, how do we characterize AI, machine learning systems? So for example, let's say I go and I tell you, look, I have this amazing box and it recognizes everything that you show you. And the question is, how do I specify when my box will fail, or under what conditions it provides accurate recognition? And we don't have any of those things. All we know is that I trained this system using millions of images, and I tested on images that it has never seen, and I have an accuracy of 90%. And what I can't categorize is what this 90% it is succeeded. What is the characteristics of these 90% that it was able to do that? I cannot tell. In a mathematical way, I cannot characterize it. I cannot specify when my AI system is going to fail or is not going to fail. All we are doing is it is doing better than any human being, and therefore it should be usable. That is the level we are right now. So question is that how do we make our AI systems robust? Robust in the sense it should be able to work in all conditions. So, for example, I remember, when I was a student, one of my professors telling me that I think one of the British Airways pilot was flying over Indonesia, and apparently at that time there was a volcanic eruption, and therefore a lot of volcanic ash was, fairly high in the sky, and it is basically making the jet engines clogging. So what the pilot realized is that the only way he can save his plane from the jet engines to fail is to turn them off. He actually switched them off, let the airplane glide through the dust, and when the dust particles reduced, then he was able to restart the engines. The question is that this scenario would have never been practiced on an AI model. If you haven't shown that kind of situation, you would not be able to fly that model. And the question is that maybe this pilot must have well educated with physics and understood that this is one way he could avoid this particular situation. The question is that how the pilot, or he or she acquired that knowledge, we don't know. The question could be, it is the basic science he learned in his college days and was able to spontaneously apply this technique. So this is a big problem we have, like, how we can make these systems reliable, robust, and also like any other software system, AI systems are very prone to attacks. And question is, how do we protect these AI systems? Next slide, please. Okay, so first thing is that there is literally exponential growth of data with the spread of internet, the web, and the multitudes of automatic data generation devices. And they can collect, satellites continuously transmit information of the atmosphere. And you have all these telescopes taking huge amounts of information. And I remember this kilometer array radio telescopes that are spread. And I understand that they collect each day the amount of data which is equivalent to the whole internet ever collected, or something of that order, phenomenal order. And in fact, they can't even store them. They have to process real time and only keep information that may be useful. So we can collect we produce data that we cannot store anymore. And in fact, people say that you have 3 levels of complexity. One is you can generate huge data, but you can't store them. But you can store the data, but you cannot erase them, because erasing data is more expensive than collecting. The question is, when you want to erase, you need to know, is it safe to erase the data? And that's why, if you look at in anyone's computer, you have so much junk in it, because we don't know whether I should be able to delete this file. And the moment you delete the file, you realize you made a mistake. So as a result, we tend to leave the data, deleting information is more expensive than collecting. And of course, collecting is more expensive than generating. So we are in that situation. It is truly exponential. The trend is going to continue foreseeable future. And the reason I said it is continue in the sense that with finite resources, nothing can ever grow exponentially. And I tell my biologists, even the bacteria cannot grow exponentially. Eventually, you run out of energy to feed this bacteria. So the same thing happens even with virus. So everything will end eventually, but in the foreseeable time, it is going to be growing at a phenomenal rate. Next slide, please. Okay. So for example, terabytes a day an MRI machine can produce these days. The next generation sequencing, metabolomics, all of these life sciences, they produce huge amounts of data. So for example, in 2012, I haven't really followed recently, but in 2012, they assumed to have a full genome of an individual is about $1,000. So now that is probably less than $100 to sequence a human genome, cheaper than taking an MRI image. Next slide, please. So the idea is that you can produce data quite cheaply. Next slide, please. Now, the problem with many of the rich, complex data sets is they have high dimensionality. In computer science, there are 2 curses. One curse is the dimensionality. That curse of dimensionality means that many problems becomes exponential in their nature, we just cannot deal with. And the second is, if the dimensionality is very high, the quality of data degrades exponentially. And the reason is that the amount of information you need to collect for high dimensional data grows exponentially. just to give you a simple example, let's say if I have a coin, I have to decide, what is chance of, if I toss it, chance of seeing a head or a tail. All I have to do is maybe toss that coin about 100 times, and then I can say, oh, looks like this coin is somehow biased. 40% of the time it shows head and 60% of them tail. So by just running an experiment about 100 times, I can tell that. Suppose, let's say if I have 10 coins, but somehow they're correlated. Let's assume this is basically some kind of a connected coin. Then to get its statistics, now it is 2 to the power of 10 possibilities. So each possibility, that means 2 to the power of 10 means 1,000 possibilities. And each possibility you have to, let's say, assume at least 100 times you have to measure to predict that particular sequence to come. So you're talking about 100 times 1,000. So you can see how it is exponentially growing. So if you have 100 coins, you're talking about 2 to the power of 100, which is probably larger than the number of atoms in the universe. So you can see very quickly the dimensionality makes your data useless. The larger the dimensionality, the usefulness of data will degrade exponentially. However, if these dimensions are not completely independent, then it's not a problem because they're correlated. So therefore, even if the dimensionality seems to appear, intrinsic dimensionality may be low, and therefore I should be able to use the data. And this is generally what happens in many data sets we see in, let's say, in medical. For example, many genes are co-regulated. So even though there are 30,000 human genes, because we know that they're correlated, we don't have to worry too much about that dimensionality. So the question is that the dimensionality is a big curse for computer science, AI, and understanding. And the other one is, as I said, you need more data points. The higher the dimensionalities, higher the data points means more storage is needed, and computation time also tend to go with the size of the data, at least a quadratic or a cubic, but with the dimensionality, it tends to go exponentially. So just to give you an example, the current, I think, population of our Earth is 8 billion approximately. And let's say if we collect the genome of every person, that's about 3 billion DNA sequences. And then, of course, we need to collect many other aspects, functionality of those genes and many, many other features, like, the person's age and how they are related to other people. All of that information, it basically goes very large. And similarly, you can see, like Amazon, eBay, all of these people collect huge amounts of information. And these informations tend to come in different formats, as we talked about, like sequences. It could be spatial, temporal, graphs, streams. There could be natural images. There could be medical images like X-rays, MRIs, and there could be video. And sometimes there could be, truly three-dimensional and audio, stereo, and combination of all these modalities. That means they are synchronous. So video and audio, they are somehow correlated in time, and that has to be taken into account. All this data can be processed and can be used in applications. Next slide, please. So, but the problem is that, as I said, we can collect the data, we can produce the data, but we cannot collect and store it, and we can't maintain it. And computational methods cannot handle this magnitude, as I was saying, especially with the increasing dimensionality. And therefore, we need good algorithms. That means, curse of dimensionality cannot be solved unless they are correlated dimensions, which means the real dimensionality is lower. And like, for example, the traditional principal component analysis relies on that, in the sense that the actual dimensions are much lower than the real dimensions that we measure in the real life. So we need good approximate algorithms. Like, for example, today all the AI models are approximates. Like, for example, we build this deep neural net, but it's an approximate model for two reasons. One is model itself is approximate. On top of that, the optimization we do is probably suboptimal, because the real optimal one is NP hard. We can never compute them. So we use some stochastic gradient method with some good heuristics and hoping that that would do a better job for us. On top of that, we need better computing infrastructure. So we need without GPU machines, I think today's AI would not be in the same state that it is now. So GPUs made a breakthrough for AI today. So, for example, now I think that China is talking about building. I forgot the name of their model. They're trying to build, something like GPT-3 kind of a model using 2 trillion parameters. So it is almost approaching the size of a human brain in some sense. I think we have something like 3 billion neurons and a connectivity of something like 10 to the power 4 connections between two, from one neuron, a fan out of 10 to the power 4 connections. But apparently this is, reaching that level of human brain, and they're trying to train this model both with many, many languages and images and all kinds of data that they get on the internet effectively. Now, hoping that once they train this model, then these models can be used in many applications. And of course, these models can only be trained by GPUs. So for example, I think, some of the estimates were saying for GPT-3, for training this one is something between $3 million to $12 million of money spent just for computational time, not the time it required to train the model. So the question is that decision makers like our politicians or executives, if they want to make good decisions, we need good hypotheses to make the decisions, and these hypotheses have to be backed by good evidence, and this is where AI plays a very good role. Next slide, please. Okay, so from a computer scientist point of view, we think we have done a pretty good job with data management. So for example, you can see examples of that. Today's Facebook or Google, Microsoft, all of their devices basically use typical computer science technology, how to build large-scale systems, how to store the data properly, how to build redundancy, how to build, some kind of encryptions, how to make these data consistent. For sometimes the data is distributed, and CAP theorem tells you can't have consistency and partitioning simultaneously or accessibility. So then we sacrifice one of these systems and try to build reliable for their medical, then going to a proper doctor and actually consulting, which can be quite dangerous. And we know how to build these systems. The algorithms are well understood, and the computation, we can do that. And we can have some reasonable security and privacy for the traditional computer science. For machine learning and data mining, again, issues are scale. Like I told you, that the dimensionality is a big problem. And data modalities, even in traditional database systems, we need to do with relational models and maybe graph models, maybe sequences and so on, we can do it. But we are generally in the database management, we tend not to, for example, process images, that no database technology can do face recognition, and we rely on AI machines. So even AI machines sometimes have to deal with relational graphs, text, and so on. And we need to discover models that fit the data. The question is, what is the best model that I can train using my models? For example, if my data looks like a graph, what is the best model to use? If it looks like a relational database, should I use a deep neural net, or should I use some very good XGBoost or decision trees and so on. So the question is, what is the best model to use? And again, we don't have a priori any heuristics or understanding what is the best model to use. What we do today, try various models and see which one works best, and then go for it. The security and privacy is much more difficult in AI systems than the current traditional systems. So when I say security, what I meant is that can we somehow break these AI systems much more easily? And the answer currently is yes, you can. The privacy, so for example, you build an AI model, is somebody able to infer what data is actually used in building this model? Again, people are looking at various kinds of encryption models and data privacy models people are trying to use. So the applications of AI is basically unlimited. So like, for example, traditional computing, we had roadblocks. For example, traditional computing can't be applied for, let's say, for recognition or language translations. They all failed badly, even though they made a reasonable success initially. For example, image processing was done very traditionally. People used to do statistical analysis, find the mean value, find the entropy, some kind of structure, apply various filters, and then use those coefficients, and then trying to use some simple rules to recognize this is a cat, this is a dog. And those failed miserably, when applied much more complicated situations. Whereas the AI models based on deep neural nets have done phenomenally well. So now a combination of traditional computing and the AI models basically open much wider scope for unlimited applications. Many times people don't realize this is actually property of computation. I always tell my students that if a human being knows a procedure how to solve a problem, and that procedure could be encoded in a computer, which means you can solve any problem any human can solve. And the question is, the human doesn't know how to explain how he or she is solving the problem, then of course we can't translate that knowledge. So as long as we have knowledge, we can encode them. And that is the state of the art of the traditional computing. But now with the AI, not what we're trying to do is that based on examples, we're trying to infer some knowledge which we may or may not be able to explain. So I didn't fully see the text. There was some question, I guess.
Sir, we can pick up the questions at the end of the session.
Okay, that's
yes,
great.
Yes,
Thank
that
you.
should be better.
Okay. So the question I was trying to say is that the applications are unlimited. I mean, I will be mind-boggled every time I see somebody saying that we applied this deep neural net, the results were amazing. Just to give you one simple example, prediction of earthquakes was just about impossible. And that's why you see every time so many, thousands of people will die because we are unable to predict. However, the secondary and third earthquakes are much more reliably predicted using deep neural nets than any computational methods that geologist knows. So for example, I give you examples in my talk later that there are complex problems for which we have perfect knowledge, but computationally we can't compute them. And that's because of the complexity of the model. So for example, for earthquakes, we know everything, how the, it's just the Newtonian mechanics, pressures, and maybe some non-Newtonian physics also will be used, like, there may be viscous materials and so on, but we know all the maths. But the question is, we don't have enough information to collect completely the model of that part of the earth, and therefore cannot predict when the earthquake is going to happen. However, using deep neural nets, people were able to predict the second and third type of earthquakes, how severe it would be, at what time it's going to happen, apparently is much, much more accurate than current physics models. So that shows AI can solve many, many problems that current physics, even though they know the model, cannot predict reliably because of the complexity of the model and not able to use the data that they have very accurately. Next slide, please. Okay, so some of the breakthroughs, like for example, the chess, I think the grandmaster was beaten a long time ago. I think IBM Blue Machine, I think, I forgot the name, but it's basically very traditional type of computing, because you know that this game, you know the rules, how to move these pawns. And basically what we do is we play all possible sequence of certain depth and then use some heuristic function which says which move is most likely be the most beneficial. That's how they built initially, and that already shown that it can beat some of the best players. But at that time, people thought the Go was so difficult, it is almost impossible to win a best champion that can play Go, shown on the left side of the image. By the way, I don't know the rules, but what they say is that it is much more complex than chess program, because the possible moves are many, many more than the chess would have at any given situation. So as a result, they felt that for next 100 years, based on the current AI progression, that no computer program will ever beat a champion of Go. But then the DeepMind people started building Go using basically deep neural nets used to with reinforced learning. They basically trained the model and beaten, I think, in 2018. And if you're interested in this, you should watch one of those amazing videos that show how this game is played. And you can see that at the end, you feel disappointed because it actually destroys the human spirit, that somehow our brain is somehow so much superior, was actually shown to be, at least in this context, not as superior. And AlphaZero now can outplay any player of Go and chess. And also there's another game. And this is a very generic game and is simply learned with no training in the sense, no expert trained it. It played against itself and became an expert. So this is a remarkable achievement from an AI point of view. And next slide, please. The next one is protein folding problem. Again, in life sciences, this is one of the hardest problems to solve. So for example, our body basically functions because of various proteins we produce. Apparently, our brain produces, I think 30% of proteins are needed for our brain to function properly, more than 30%. So these proteins are produced as a result of the genes we have. So a protein can be seen like a string of some alphabets, and this alphabet comes from 20 alphabets. These are called amino acids. So this is a sequence. Unfortunately, the sequence doesn't tell us very much from a functional point of view. So this sequence in our body forms into initially secondary structures. The first thing is like a coil, as shown on the second row left diagram. It's like a spring. Or the sequence could fold like a sheet. So for example, like A1, A2, A3, A4, and then it switched back, then A5, A6, A7, and then switched in the other direction. It forms like a sheet. And these are called beta sheets. And together forms a tertiary structure which looks like a spaghetti containing springs and sheets. Now, this complex tertiary structure will interact with other protein, and then that allows our body functions. So this is what makes us behave the way we behave, both in terms of vision, thinking, building muscles, everything. Your whole body entirely depends on this. But the interesting thing is that all this information is just available in that sequence, the primary sequence, just string. But we don't know how to go from that sequence to the final structure. And this is one of the open problems in biology, protein folding. And again, the deep mind people from Google, they built this something called AlphaFold 2, and it is doing as accurately as one of the best protein folders you have. Every year they have something competition. I think it's called CASP. Basically, what they do is they provide sequences like this, and then ask people, give me the tertiary structure. So now this AlphaFold 2 is winning more than any lab or any individual using any other techniques. So typically they say that, if you have a complex protein with, let's say, argument's sake, 1,000 alphabets of amino acids, that is 1,000 amino acid long sequence, to fold that, you might have to spend maybe a year or two to using crystallography. That means, first of all, this protein has to be somehow made into a crystal, and then you bombard that using some X-rays, and then the reflector light, you do reverse mathematical computation, and then basically understand where the locations of these amino acids are. Based on that, you actually build a three-dimensional structure. And now this AlphaFold is doing in few minutes or few hours. And this is going to give you an amazing tool for biologists to treat various kind of diseases, and even to build new kinds of drugs based on these kinds of understanding the structure of the proteins. Next slide, please. All of these are because of the AI. So typically this is what the AlphaFold does. You're given input sequence, and then you have this deep neural net, which produces the three-dimensional structure as shown on the right side. So this is a real breakthrough. The next one, please. So this is my students and we did this work. Here, what we have done is, you take a human brain, a three-dimensional, diffusion weighted MRI picture. You do basically what the diffusion weighted MRI is, that how the water molecules are moving in your brain. So for example, let's say if you have a container that looks like a skull, but there's no, let's say, neural matter here, only the fluid there, then all the molecules, all the water molecules basically have Brownian motion. But once there is a brain in there, then the brain makes the abstraction to these water molecules. The water molecules can't go like a Brownian motion. So wherever they are there, they will be abstracting. Therefore, the pattern of the way the water molecules move will be different. And this MRI can actually measure the movement of these water molecules, and this is called diffusion weighted MRI. So the question we wanted to know is that, knowing the movement of these water molecules, can I predict the structure of the brain? And once I predict the structure of the brain, can I predict the function of the brain? That means, can I tell how your brain is functioning? And we were able to do that. Not fantastically accurate, because no one can do using any techniques, but it is doing better than any techniques that is there. So we were able to do that, this kind of functional structure, using deep neural nets by training them appropriately and having correct loss functions. One of the things you have to remember is that there are so many AI models that you have, but the real trick is that what kind of loss function you use. That is, loss function is effectively the most important part of your deep neural nets. How you define your loss function makes your neural net how good it is. And of course, to to have a very good behaved model, you need high quality data. Without that, you don't even try to build anything. And once you have that, then you have to have appropriate structure of the model that you're trying to train. Should it be ResNet, or it should be traditional convolutional neural net, or should it be a transformer network, whatever that is. And then you also need to think of what kind of loss function I want to have. And loss function, all these three things together with appropriate optimization, you would be able to build a very high quality network. Any one of these three goes wrong, you will never have a proper model. Okay, go to the next slide, please. So another thing we also did is that, this is the computational fluid dynamics. So one of the things we were looking at is that, as you age, we all have some problems with our heart. Basically, the blood circulatory system at the heart is not doing well. The arteries are not working well. And it's kind of strange that, the blood is there in the heart, but the heart is not functioning because there's no blood, which is kind of a strange contradiction. And the reason is that the blood rich in oxygen has to be supplied to the blood vessels. Even though the heart is pumping blood, but it needs the right kind of blood to its blood, its muscles. And these are supplied through these veins. And as you can see, this is one of those blood vessels that is showing the red indicates high stresses. That means the blood pressure is very high at those walls. That means the pressure on the blood vessels is very high. That could be very narrow area or some kind of a plotting area. Now, the question is that when a surgeon is trying to put a stent into them, they needed to know where to put stent and what size, and some of these issues are needed. One of these ways to do is that while the procedure is taking place, they will send a little probe, which is called some kind of optical coherent tomography. Basically, it's a slight laser beam sent, and the reflected light, you measure it. Based on that, you can actually tell the blood vessel thickness, the shape of these three-dimensional shapes, you can measure it. And once you measure the three-dimensional structure of this vessel, then you needed to see how the blood flow will be like this. This is where the computational fluid dynamics mathematics would come in. But the problem is that to do this computational fluid dynamics properly, I was told by my colleague, co-researcher, that it would take to do very accurate prediction about 3 days of computation. Then I told him that why don't we do some deep neural networks and we train these models, they should be able to predict very well. And we actually done that. And we found that our results are pretty accurate to nearly 95% accurate. That would take 3 days of computation, we can do under a minute. So that means while the surgeon is doing procedures, we can actually tell you the pressure on the blood vessels. So the square diagram shows you, if I unroll this blood vessel as a sheet, it shows you, for example, the left side blue means there's no obstruction, and then you see obstruction is increasing, and then deep red shows you a lot of obstruction, and the rightmost is very high stresses. So it is actually showing the stress levels. Unfortunately, we haven't published this result yet. The student, unfortunately, the student's father recently expired because of the cancer. So he decided to spend his time to look after the family because he needed to earn money for the family. Sadly, we haven't really published, but the results was truly astonishing. Go to the next slide, please. So basically what I'm trying to show here is that by using these AI models cleverly, you can solve many, many difficult problems. For example, we can produce new paintings, and you can compose music. You can even write articles on certain topics using GPT-3 and so on. And people are saying it's very difficult to say that this is computer-generated text, and people are questioning, how do we stop plagiarism? Can maybe this, situation has come. Students can use tools like GPT-3 or Bloom or one of these things, and then basically produce answers without really understanding, and then submitting, and then we as instructors would be unable to tell whether it's real or fake. So this is a big situation, and I think the deep fake is a problem we're going to face very soon. So the current trend in AI is you probably all of you know, is foundation models. So it's basically like software engineering. What basically they're saying is that you don't have to learn models ab initio. That means you don't have to collect all the data to train your model. So the idea here is that we basically pre-train these models using various deep neurals that we understand well, and these learned models will be adapted to your new situation, to new problems. So this is basically transfer learning. So basically what you do is you take one of these existing models that are learned, let's say, for example, BERT or GPT-3, you take it and you throw the last layer, whatever the layer that they used for training, to fit this model perfectly. And then what you do is the last layer you build with your own, let's say, using softmax final layer, and then you train with your data that final layer. And this, the trained data that you have, it doesn't have to be large. Maybe even a size of few 100,000 is enough. Whereas if you have to do ab initio, you might have to need several hundreds of millions to get the same quality. And this is what the foundational models basically advocating, that you can use something like GPT-3, Bloom, and BERT for language models. Like, I understand Bloom understands about 19 Indian languages, including my mother tongue, Telugu, Tamil, Kannada, and I'm sure definitely Hindi and maybe even Sanskrit. It can translate to other languages effortlessly. And also it has been trained some computer programming as well, can produce simple, web programming and so on. I understand, and I haven't played with any of these tools, but understanding, reading their research papers, they're doing very well. And similarly, DALL-E 2 is for image recognition. So these are the basically fundamental things. It's almost like in software engineering, we use libraries. Like, for example, you don't write a new package for matrix inversion, or you don't write a new package or a new library to do principal component analysis, or you do some tools. For example, let's say for building, let's say, linear regression or something, you don't write the code. You take the package and you basically push the data. But here, these foundation models, what we're saying is that even pushing some of the data is already done in these models. That means some of the parameters are already set in these systems, and then you can only need to specialize these models for your specific need. But sadly, these models are not practical at large scale. What I meant large scale is that, let's say I want to build some application, I can't just use it because these models are too large. You need huge computing infrastructure. And probably one possibility is some having some GPU clouds, and you don't need to train these models because they've been trained already. For real hardship of training is already done, and you take this model and all you're doing is the transfer learning, and that's only a small part of the training, and that costs money as well. But once you have done that, maybe the use of that final model may be a lot cheaper. And that's what they have done, for example, with AlphaZero. AlphaZero, I think, was trained on a huge machine using probably 5,000 TPUs. But when it's actually playing, it was only played on a 4 TPU machine. A TPU is basically tensor processing unit, like GPU, but tensor means it basically does the matrix multiplications and so on, and convolutions. So these are special form of GPUs, and GPUs are just as good. So this is what will happen. And the question is that the current models they're building, whether they could be run on a, let's say, we all can, for example, can afford maybe 4 TPU machine on your desktop, which is probably not too far. So that means we should be able to use these models, provided these models could be incorporated into those smaller machines. Next slide, please. So some of the challenges that we find in AI is the data acquired may not be complete, even representative of reality of AI model to behave reliably in all situations. So this is a very important statement to digest, and I'm sure most of you know this is an unsolvable problem. It will never be solved. That means, do I know everything I need to know? This is the question you will never be able to answer. So this is almost like an undecidability or Gödel's incompleteness theorem kind of situation. So when you collect the data, for example, if I collect the data, do I know how good this data is? Probably not. I can tell in a hand-waved sense that, look, this is unbiased, we did randomly, and so on. And this, again, my perception that I've done well, but the model itself might say this is not the case. So for example, today, we have amazing theories in physics, general relativity and quantum mechanics. They are completely different beasts. And then we find these observations like dark matter and dark energy. None of these models explain it. We don't know where this is coming from. And for example, in quantum mechanics, this notion of collapsing wave, and that is not understood. That is completely open. The moment you measure a quantum system, the entanglement is collapsed. So question is, what physical process happening? Nobody knows, and that cannot be explained. So there are so many gaps in our models that we build, even though they are amazingly accurate models in predicting many things. So for example, to date, we did not find anything wrong with quantum mechanics or anything wrong with general relativity. And yet, we have phenomena that neither of them can explain. For example, gravity at the quantum level, we don't know what it means. Is there a particle that somehow, defines gravity? So there are many unknowns with all these models. So what we have to remember is that all these models are approximations. So similarly, when you collect the data, you don't really know that data is actually representing everything that the model is trying to produce that kind of data. So the question is that the model that we built may not be the real model. Like quantum mechanics is not necessarily the model of physics today. Today, that is the best model that we have. That's all we can say. It is a model. It is not necessarily truth. Okay, so this is a problem that never be solved. So therefore, any system we build is always questionable. Is it always going to work? We can never categorically state that. Okay, so the only time you can say is that, so for example, let's say I build a program which recognizes whether the number is a prime number or not a prime number. So there, my knowledge is complete. I know the definition of a prime number. I can code to check the number is prime number or not. I can guarantee you my program works. Whenever it terminates, it gives you the correct answer. If the prime number is tremendously large, the universe might end, but when it gives the answer, it gives you the correct answer. There, I know the model, and therefore I was able to write the code correctly. But the question is, when I don't know the model, then however much of information you provide, my model would be an approximation. So that's what the AI is. Like the one example I gave you, the pilot who was able to save the airplane is because somehow some knowledge he had, he was able to apply at the right time to switch off his jet engines and then restart them when he was away from the volcanic dust. So this kind of scenarios we cannot foresee in our AI models. So that's the first problem. That means incompleteness of data quality, that this is an impediment on our AI systems. The second one is that we have collected so much of knowledge. Sometimes our knowledge that we collected may not be consistent with the data acquired. Classic example, quantum mechanics, we have all of this knowledge, and then we acquired the knowledge that tells you somehow the galaxies are accelerating farther away, accelerating faster. So general relativity doesn't predict that, neither quantum mechanics. We don't know where this dark matter coming, we don't know where the dark energy coming. Quantum mechanics can't tell. We have an observation, but the model doesn't explain. So you see that huge amounts of data we collected. Again, this knowledge is also incomplete, because what is the knowledge? Knowledge is again a model, that is, human-built knowledge. We call him as our understanding of Newtonian mechanics. Newtonian mechanics was everything that need to be known. Like until early, late 1800s, people thought whole physics is solved. We were able to predict exactly where the planets are. We were able to predict seasons. Everything very accurate. There's nothing more to know about physics. That's what they thought. Then came quantum mechanics. Then came general relativity. So all of a sudden, we came to the conclusion that we didn't know very much. And when they progressed to a large extent, then they realized that we have more or less understand everything about the universe, including Big Bang and so on. And then finally, they recognized this is the dark matter, dark energy. We don't know where they come from. And we don't know what exactly happens within the black hole. All of these issues basically tells you our knowledge is also not complete. However, we do have a lot of very useful knowledge that we can apply in our real life. It could be in sciences, engineering, economics, social sciences, arts, music. Everywhere we have a lot of information. We have both in terms of data as well as some kind of rules. So question is, how can we use this knowledge in AI models seamlessly? Somehow we need to integrate this knowledge into these systems. Again, this knowledge is also not complete, as I said. Okay, next slide, please. Okay, so as we, probably you have gone through these things many times over, but the models that we kind of very happy, I didn't put reinforcement learning here, but reinforcement learning also uses some of these models. Basically, you have these convolutional neural nets. Basically, this is the effectively, main breakthrough that AI was able to do that in terms of recognition of images, better than human beings, and immediately applied into language models. And then recurrent neural nets, which is a kind of a effectively convolutional neural nets, but in a recursive way. Then the transformer networks came and attention networks that made these networks much more robust and reliable. And the ResNet, all of these are the basic models that we use. And again, as I told you, this is only the structure. We need to have good quality data. And the important thing is what kind of loss function you would use in training these models. So as I said earlier, all these foundation models are built using some of these structures, and they have huge access of data as well as computing resources to build these models. And then basically they make these models public, or at least you pay and you can get the models, and then you take these models and adapt to your applications. Now, question is, how can an AI model explain the reasons for its decisions? So one of the important things that we humans want is that not only we are interested in the answer, but we also wanted to know what is the reason for that answer or for that conclusion. Without that, we never be comfortable with those things. So this is very important, both from a legal point of view, both in advancing science point of view. So for example, let's say you trained some interesting deep neural net to recognize, whether this person has a disease or not disease. Let's say it is 100% accurate, but it doesn't help us because we need to understand underlying physics or underlying process or chemistry to understand why these particular aspects makes this person is suffering from this disease, or why I should make this decision at this point to avoid the accident. Some of these explanations we are needed. So we needed to somehow, the explanation aspect have to be built into these models. And on top of that, we also need to add this domain knowledge into these foundation models in a seamlessly, rather than take these models and then build some more complex systems is much harder. One possibility is domain knowledge through the loss function. Remember, I keep on repeating, loss function is very important. Loss function basically tells you what am I trying to make my model to behave properly. So for example, in the case of image recognition, you say, well, I'm interested in for it to recognize accurately whether it's a cat or a dog or a human being, whatever that is. So that is what I'm trying to minimize. Maybe in other applications, I'm not interested not just what the images are, maybe I'm also interested in the levels, like for example, what is the level of intensity of a particular disease. I'm more interested in the intensity, not only just saying the person is suffering from this particular disease, but how acute this infection is, and also explanation and what treatments that I needed to do. This is the level of thing. The loss function may be very different. So one way I can include my domain knowledge is incorporate the domain knowledge into my loss function using maybe set of constraints, how various features are related. So for example, let's say, argument's sake, an image is there and you have an animal in there. And if during daytime, you will never see that animal because it's nocturnal. It only can come during daytime unless it is dead or something. So pretend we're only thinking of live animals. So it is moving. We know that it is alive. But it's daytime. It's a nocturnal. So domain knowledge tells you an nocturnal animal cannot be visible during hot day. And if we know that the image tells you the temperature is very high because we have fed that information, and the domain knowledge tells you this object cannot be that animal. So when my model predicts that, my domain knowledge tells you it cannot be this. So that means it could be an artificial animal, not a live one. Maybe that kind of explanation can be built into the loss function, incorporating that domain knowledge. And another one is, for example, let's say you're building an automated car and the domain knowledge tells you on the street, the speed limit is only 40 kilometers an hour. So if the system tells you you can go 100 kilometers an hour, then the domain knowledge tells you on the street, you are not allowed to go 100 kilometers. So the decision the system made is wrong, and therefore that loss has to be minimized. So some kind of domain knowledge can be incorporated into loss function. So we know, for example, a loss function can be modified with constraints using Lagrangian optimization, for example. Go to the next slide, please. So here, that's what I'm trying to show you, how I can incorporate domain knowledge. So for example, you have a deep neural, you have input. Data collection is generally easy. As I told you, collection is easy. Maintaining is much harder. Data annotation can be very expensive. So for example, the crowdsourcing helps a lot. In some cases, annotation will be very expensive. Suppose if you have medical images, only the medical trained people can annotate those data. and the domain knowledge as constraints in the loss function. So for example, here I have input, deep neural net comes in using some foundation model. And then in the next layer, this is a specific prediction layer that I'm trying to put for my data, which I will make it learn. And then the red box is the loss function that minimizes the model. Best parameters are estimated for the model. Let's say if it's the classification one, then the loss function not only minimizes the error of labels, that is misrecognition, and also puts the constraints based on the domain knowledge. So for example, as I told you, during daytime, you don't see this kind of animal, for example. That kind of knowledge can be built into, if it predicts during daytime, you're seeing this particular animal which only lives in the holes is completely wrong and therefore minimizes that error. So this is one kind of model. And to my knowledge, no one has built any of these things yet. This is still pretty new in my book. Next slide, please. So the another suggestion I have is that how we can provide explanations. Again, you can see you have input. Again, apply one of your foundation models that you can apply. If it's a language model, you might want to use something like BERT or GPT-3, or if it is an image recognition, some kind of a ResNet or CNN or a transformer network you might use. And then the next yellow box or orange box tells you that you need to build a prediction model for your data. And then I put this kind of purple color is the explanation box. So for example, let's say I might have some annotations for my data saying that, so in this case, I call this cat because I was able to see certain properties. And these properties can be computed for those examples that I can use that. So the interesting question is that these explanations are coming from actually there's an arrow wrong here. The arrow should be from the input to the deep neural into the explanation network. So basically what we do is we provide input directly to that and then try to build a loss function jointly. Okay, so here, not only we try to minimize the error in recognition of the object, but the explanation also has to be correct, whatever the explanation is. So for example, let's say our input has, let's say, it's a balloon, helium balloon, let's say, we expect it to float. So the explanation is that because it contained helium, the balloon will float. That is the explanation that this box provides directly from the input, from the green box to the purple one, and then loss function has to make sure that explanation is actually predicted by a model. If not, then you propagate and then retrain this deep neural net for the explanation. So you can do that. Again, the expensive part is that how to build these annotations for explanations. So again, each input needed to not only come with a label, but also some kind of explanation. So for example, in the medical cases, many times the doctors would give diagnosis and also explain the reasons how they came up with that diagnosis. They might say, because you have this disease, because I have seen consistently over 5 days, your blood pressure is very high, your blood sugar level is very high, and so on. And because of these reasons, I believe you have this particular disease. And this is the explanation that is written in language, and that could be used in your loss function to see whether same language annotations generated for this prediction. If not, the model will be through back propagation, it would train. Next slide, please. So in this case, I'm now introducing not only explanations, but also domain knowledge. So here you can see that the input, a solid arrow going into the deep neural net, and a solid arrow goes into deep neural net. Again, a little bit errors here. I think the first level have to be, again, dotted arrows, because back propagation does not change the input. So wherever the solid line is there, back propagation is allowed. Okay, the first two arrows have to be dotted line, and deep neural net will be continuously, given foundation model we can use. The domain knowledge, again, solid line comes into domain knowledge, again, dotted line, and that's fixed. And then we produce some results, and then they will be fed to the deep neural net and also deep neural net for explanation. And again, you can see that I just modified these things badly. Again, one of the inputs from the domain knowledge to the deep neural nets, that is correct. You can't back propagate. So that means domain knowledge is fixed, and explanation network can be learned. And you can model, based on the explanation as well as the specific knowledge we learned, we can modify the deep, the foundation model or the deep neural nets we have. So again, the red box, which is the loss function, which controls the accuracy of the explanation and the classification. As you can see now, we have some hope how to seamlessly incorporate domain knowledge. Basically, what happens is domain knowledge provides a higher level of inputs into the deep neural nets. And if you spend some time in the deep neural nets, as you can see that as you go to the higher levels of the deep neural nets, the final layers, it is always going to be fully connected network. That means we don't have any more locality. Now the information is global. That means every node, every deep neural, hidden layer node has full knowledge of the problem now. So we're not doing any more convolutional neural nets or any more attentions on them. Now we are completely relying, every node has a full knowledge. Similarly, domain knowledge will provide such kind of nodes, and then based on them, you build the deep neural net. So the knowledge is not modified based on back propagation. This is what we learned. Whereas the deep neural net, the first box of deep neural net can be modified. The second deep neural nets can be modified as well. And the classification output is basically our decision. And the loss function is the one that actually incorporates how much of error we are making on the explanation, how much on classification we do. So this is a good way of building a reliable domain and knowledge. And the hope is that there may be a contradiction. The data tells you through deep neural net, it tells you it's a cat, and the domain knowledge tells you it's not a cat. Now, question is, depending on what we value more accurately, our loss function might give higher weight to the domain knowledge-based error compared to, let's say, deep neural net, in which case the knowledge takes over the control, and that's how the deep neural nets will be modified accordingly. Next slide, please. Okay, so in this is the final one that I have, is that you have many more interactions taking place. That is, the input directly goes to the deep neural net for explanation. Again, that is not back propagated, direct input, and similarly direct input to domain knowledge, and again direct output to the decision layers of your deep neural net that you're learning. So here, the solid lines are the lines that we can learn, that is back propagate them. Anything dotted lines are frozen lines. They only provide input. And I think, in my view, this is the ultimate network that we needed to build, very large scale. If I have something like Google kind of funding, I can build this model, and we can try on very large, interesting problems where the domain knowledge can be encoded using. Again, sometimes this domain knowledge can also be trained using deep neural nets, in the sense that the domain knowledge may be written in some kind of mathematics, or it could be written in some language. Somehow that need to be represented in a computational sense. So some of these things, again, an open kind of questions. So next slide, please. Okay, so the question is trust and security in AI systems. How do we characterize AI systems? And I already alluded to that. I'm not going to spend too much time. That we don't have a way of explaining what my AI system can do or cannot do. I don't have any specifications. So for example, let's say if you buy a car, for example, it only accommodates 5 seats, 1 driver, 4 passengers. It might also tell you what is the maximum speed it can go. It can also tell you how much load you can take. It also tells you how good the brakes are. So you have some idea of its specifications, and they're pretty accurate. And similarly, I might have written a program that tells you whether the number is, divisible by X. I can guarantee you it is going to work all the time, irrespective of the number, irrespective of the value X. I can give you complete specifications for an image recognition system. What specifications I can give? Nothing. All I can say is I trained on this, this variety of images under these conditions, and I tested these under these conditions, and it works. And the medicine is like that. Today, all these COVID vaccines that we give, all we know is that we saw that, if you have this vaccine, this much percentage of people are not infected by the virus. And we know that breakthroughs are happening, people are reinfected. When I was young, I was told that once you get a disease, you won't get the second time. But now we know that the virus can mutate so fast that the immunity you built for the first virus may not be good enough to protect you, its variant. And we are seeing that all the time. And therefore, they ask you to take, a different kind of vaccine or boosting and so on. So the same thing is also true for large software. Like, for example, when you build a large software systems, you can't completely give it specifications. You might give specifications, but they are not guaranteed. There are bugs in the programs. Many times they don't predict. And I remember at Melbourne University, this long time ago, we were paid twice on one day, because what happened is one of these programmers reran the tape apparently second time. So we all got twice salary for that month, and it was all deposited in the bank. And the problem is university can't take the money back because they can't instruct the bank to give the money back. Only the holder of the account can only do that. So then they write a letter to all of us, effectively begging, can you please return the salary that we paid by mistake? So you can see that even more important programs like salary disbursement software themselves have bugs in them. So we can't always provide accurate specs. But at least we know that algorithmically, we know quite a lot. So for example, if my program, my large system uses various components, like for example, sorting or searching, I know exactly how accurate they are. These libraries have been well tested and maybe even proven using some kind of tools that they will work. So you can have much more confidence on them. But today, all the software is done by examples, just like AI, except that because we directly coded, we have some knowledge built into the system, we have this impression that our software systems are somehow more reliable than AI, but in reality, they are just as vulnerable. And that's why you see all the time attacks on all our IT infrastructures, because most of the problems we face is because our software is unreliable. People make mistakes, sometimes deliberately, sometimes for convenience, in the sense, if the system is too hard to use, nobody will use, but if it's easy to use, they are vulnerable for attacks. Next slide, please. So the question is that how do we build our AI systems at least as robust as our other software systems? So for example, your relational database systems, they're pretty good in, have shown they're pretty strong with appropriate encryptions and so on. So a partial solution, I believe, is that we need to incorporate domain knowledge, and that will protect with some kind of attacks. This is only a kind of a hand-waving answer. But again, the domain knowledge also helps us to specify this model, because my loss function takes the domain knowledge into consideration, and therefore I can maybe tell that at least how the model is constrained by my domain knowledge, and therefore I may be able to give some specifications to my AI systems. Again, this is an open problem, and we need a lot of research to somehow able to explain how good these models are. Next slide, please. Okay, trust and security of AI systems. How we make AI systems robust from attacks. This is a real problem. People can do simple adversarial attacks. You can, like for example, let's say you have these autonomous vehicles. There is a speed limit that shows you speed limit is 60 kilometers per hour, and then some guy goes and sticks some little bits here and there, and all of a sudden your AI system says, oh, this is 100 kilometers an hour, and starts going 100 kilometers an hour. And they're very easy to fool these systems right now. And the second one is fairness. Like for example, this is a big issue. Like, if you are disadvantaged, some of these AI systems basically unfairly treats you. Like for example, people say, in the US, when you go for a bank loan, they use many AI tools, and if you are a disadvantaged community, the chance of you being granted a loan is low. This is the fairness. If you're a female and if you're unemployed, if you come from a disadvantaged community, you won't get grant. Even though all other credentials of you tells you impeccable, you never defaulted any loan, you've been very good, excellent remarks, and yet you won't get the loan. And how do we build these systems? At the end, if you remember my final, the very introductory lecture, I gave you a pyramid. The last box is wisdom. Wisdom means that how do we make these systems fair and also robust? It's basically legal system. That means anybody misusing these systems need to be punished. And again, legal systems itself, not waterproof or bulletproof. In the sense, legal systems can do misjudges as well. But that's all we have. And the legal systems have to be revised, both national codes and internationally. Like, for example, having a perfect legal system in a country is not good enough for cyber systems or AI systems. Can we use image recognition to track every human being, and recognize from their walk or whatever it is, this person should not be given medical insurance because the insurance company sees this is the liable. And this is where the legal systems have to come and saying that, well, if you are in insurance business, you have no right to disqualify anybody to not to cover. If a person applies for insurance, you have to provide. This is how the legal systems have to come. So at some stage, I think our legal systems have to deal with this unknown AI beast, where it takes us. The question is, AI systems, like physics, they can be applied in any domain, in military, in health, in saving lives, in destroying lives. So the question is that finally the wisdom is the one that will give us some trust and security of AI systems. So we also need to build tools to monitor these things as well. Again, this is like a cat and mouse situation that one is trying to avoid the other continually. So I think the very fact that computing was invented, we have invented this problem. That is, the trust and security are given up on the day computers were invented. That means you were able to collect the data. The moment you collect the data, you have given up your security and your privacy. Next slide, please. Okay, in summary, we have exponential growth in collection of data and availability of data. So as long as this data is high quality, well, cured and maintained can be used for the good of society. Society enforces decision makers to make decisions based on evidence. So like medicine and policies that the government make all have to come from the data we collected. We need effective tools to manage and process this information. And I think the data mining and this cloud computing and data analytics and machine learning with domain knowledge will give us a hope to do all of these things. Trust and worthiness of information will become a major issue, as I was telling you earlier. So eventually it is a legal system that should protect us. And this is a question that I have: can computational methods ever determine trust? The answer is no. Like, for example, no virus, there is never, you can build a software that stops cyber attacks, because the attack is like any other program. So this is an undecidable problem. So data mining and machine learning tools are required for processing a variety of complex data for aiding decision making. And I think we are a long way in this direction, and a lot of good things are happening both in medicine, in even quantum mechanics people and quantum computing people were trying to use AI tools to build better qubits, even to understand whether the device is in entangled state or not, using some of these deep neural nets. So I think the scope for AI is just amazing, and you're all very lucky to be at the right time where computing is so cheap. And the other thing is, one of the nicest thing about computer scientists are they are very generous in sharing their code and their data, unlike in other disciplines like medicine or in chemical engineering. And I remember one of my colleagues from chemical engineering could not believe why we give our programs free to everybody to use. Okay, thank you. I'm done. Okay, last slide. Okay, this is can you show me? Okay, so you can read. I have my 4 of them. All right, I'm open for questions.
Thank you so much, sir. It was really informative session, and we come to know a lot of facts about AI, the different challenges, different issues in AI, as well as deep learning, deep neural nets, and I'm sure all the participants also find this session to be very much useful, particularly the research fraternity. Sir, we have questions. So we got the question even from our YouTube streaming link. I'm reading out the questions for you, sir.
Okay, that's great. Thank you.
Welcome, sir. So the first question that we got here is: using AI in machine learning and deep learning, particularly in healthcare settings, in order to solve many problems of complex data set in the life science, is it mandatory in the near future? What do you think about that?
I think I know this because I worked quite a lot in the medical area. So first of all, it's very hard. Okay, so let me back up a bit. First of all, to advance life sciences, you need 3 groups of people have to collaborate. The one is, of course, we call them clinician scientists, that is medical doctors who are interested in research, not just practice. And the second is a biologist, that means people who know the basic science. And the third one is computer scientists in AI basics. These 3 have to work collectively together. What it means is that these clinicians are able to collect large amounts of data. So for example, they are the only ones allowed to collect blood samples or tissues and so on. And the biologists are the ones who can run wet labs, like months and months, doing various kind of sequencing data and so on. And the computer scientists should be able to make use of this data, and then actually apply computational models. And all these three groups have to understand the knowledge, in the sense they should be able to communicate. So for example, if a clinician comes and dumps the data and asks me to do some processing, it means nothing. I needed to understand what are they after. And the other thing in medicine is that they don't like applying deep neural nets. It's fine for them as a diagnostic tool, but that doesn't advance the medicine. You need to understand what is happening within the biology, why certain proteins are expressed so much. You need to understand that. That means which genes are highly influenced by this particular disease. And once they know that, then there is a possibility of drug discovery or some kind of explanation. So to date, all the medical scientists seem to use very traditional data mining, like, for example, using regression tools or using decision trees or using some kind of a PCA or least partial square systems. So it's basically very traditional statistical models they're using. They are not using state-of-the-art AI. Part of the reason is state-of-the-art AI doesn't have any explanation capacities. So they are excellent in doing decision-making, but they cannot provide knowledge behind what is happening. And I think that is the current impediment with some of the AI techniques, and that's what I addressed today. So we need, for example, collaboration among these three groups, and also ethics clearance that, the data collection for medicine is very expensive. To get 2,000 samples would take them 5 to 10 years of particular diseases because they are rare, and then you have to collect them, and those patients agreeing to provide those biological samples, and then you need a lot of money to process them. So it's quite expensive business. And their dimensions are very high, but fortunately what they found is that they have some domain knowledge and they know exactly what kind of data they need to look at. So for example, let's say if it is to do with the liver or kidney, they know that particular genes they have to look at, or particular hormones are expressed, they look at those things. So they actually apply domain knowledge to investigate, and that's how they analyze today.
Okay,
I hope
sir.
that makes some sense.
Yes.
Yeah.
Yeah. The next question is genome sequencing same as big data?
Genome sequence same as
Big data?
No, I don't understand the next word.
Big data.
Big data. Okay.
Yeah.
Big data is a more generic word. It could be any data. Genome sequence has a lot of data. I just gave you an example in the sense that, let's say one day every human being will be sequenced. So cheap. Let's say it is feasible. And that shows you large amount of data. But then when you start showing their functional things, then the data explodes in terms, like, for example, if you remember the protein sequence, I only need 1,000 bytes of information to show. But to build a 3D model, you are talking, maybe gigabytes of data for one protein of 1,000 atoms or nucleic, the amino acids required. You're talking about gigabytes of data in a three-dimensional space. And if you're thinking many such proteins interacting, so each human being will produce huge amount of data, and every human being data is collected, then technically you can process, when that happens, quote unquote, you should be able to know completely about human behavior, potentially, and their medical behaviors and their, what would happen in the fourth generation of this person, depending on who they marry, you can predict their genetic sequences as well, in theory. So, there's a lot of uncertainties, but in theory that you can predict. But the question is that produce huge amount of big data. And big data can be fluid dynamics. It could be astronomy. So big data includes everything. Usually big data used with sequences, relational, graph, images, videos, and so on, everything.
So the next we get to see, can we use brain-computer interface in EEG?
people are using, various kind of signals that come from the brain to control devices. Already people are, paraplegic people can use, brain implant to control TV or, close the door, open the door, turn on the fan, shut off the fan, air conditioner, and so on. So you can communicate with them. And so potentially there is a signal, depending on which part of the, cortex you take, you can do that. Like, for example, people are using bionic implants, for cochlear implants for hearing. It's interestingly, you take the audio and you do the Fourier transforms and take those values, and directly those values are excited in your cochlear, and that makes you to hear. And the rest of your brain seems to understand the speech. And similarly, vision is done exactly the same way using a bionic implant. So in theory, that you can do that. Like, for example, people are using MRI, functional MRI. So let's say I go into one of these MRI machines, and then they show me, let's say, a hammer, and then I see it, and my brain recognizes that's a hammer. And meanwhile, the MRI machine reads the functional aspects of my image, and then you can use an AI, deep neural net, looks at the sequences, and it tells you I'm seeing a hammer, or I'm seeing a banana. So you can do that. Already you can do that kind of things.
Okay.
So it's not very sophisticated. If I'm singing a song, then it cannot write the singing, or what I'm singing in my head. It cannot do that level. But in theory, there may be signals that are enough to capture that. Whether we can do in our lifetime is a questionable, but in theory, it should be possible.
Okay. Next question is, GPU clouds do not guarantee adequate level of security with respect to access control and isolation. So how can we solve it?
Okay. To me, when I say GPU cluster, it's not just GPUs. You will have other traditional computing operating systems will be there, and whatever you need normal security protections, you have to apply those things. I mean, today, one of the things that cloud computing, people thought impediment is that if I put my data on a cloud, how do I know nobody's stealing, right? But same thing, you're happy to put money in the bank, and somehow you think the bank will keep your money. What happens if the bank bankrupts or the government collapses? So there is always, some level of unreliability. So that's why what you do is that the reputation of company or the legal system, that should give me adequate confidence that my data will not be destroyed or leaked or given to someone else. Then only cloud computing becomes. You can encrypt and put them in there, but when you're trying to process, you have to decrypt for it to be efficient processing. There are some algorithms that can work on encrypted data, but they are terribly slow, not practical. Then the quantum encryption might help you to see whether somebody touched your data. These are possible, for example. So, and I think as I said, there's one problem we can never solve is the trust. The trust is basically on our governments, on our legal systems. Look what's happened in American election. Even today, some of the people don't believe the election was fair. But, it's not one or two, it's a huge population. So I think this is a kind of a meta level question in the sense that eventually you trust on the company that is providing the facilities for you, like the way I trust my bank to put my money in there. And the bank trusts on us because you showed a house. The assumption is the government will allow them to take over the house if I don't pay the loan. So that is the trust the bank relies on the government. And the government relies that all these banks are functioning properly, therefore they can run the government. So you can see the mutual dependency for any society. So occasionally these societies break down. Look at Sri Lanka right now. So there are trust that comes, like people say, the moment something becomes civil unrest, it is very hard to come from that black hole. You can come out of corruption, you can come out of war. Coming out of civil war is very, very hard.
Okay, I think due to time factor, this is the last question we are taking up. So the question is, what is the difference between quantum computing and osmotic computing? I mean, how these two computing concepts are used in healthcare industries?
Quantum computing, what is the other one?
Osmotic computing.
Atomic computing.
The spelling is OSMOTIC. That's what.
I don't know about osmotic, but quantum computing I know very well because I studied a lot. Quantum computing gives you something called quantum parallelism. And I think that is the most important part of the quantum computing. So for example, in a quantum computing, you can simultaneously represent many states on a finite sequence. So for example, if you have 100 bits of quantum qubits, they have the potential to simultaneously represent information 2 to the power of 100. That is the quantum entangled information. And that is a phenomenal parallelism. That is basically exponential parallelism in terms of quantum parallelism. So that allows us to search the space simultaneously in all these states to look for certain properties. So that gives you exponential speedups in terms of computing power. But the problem we face today with quantum computing is that this state is very fragile. Very quickly you lose that information. So therefore you need huge quantum correction. And what they were saying is that if you want to have quantum bits of, let's say, 2000 bits, you need something like 200 million quantum bits you needed. So the error correcting bits are so large, we don't have technology today to build that kind of machine. But quantum computing, at least from a theoretical point of view, is quite attractive. And it will play a huge role. Suppose, let's say, if quantum computing is feasible today, you can build some of these AI systems incredibly fast, much larger systems, much more accurately because of the sheer power.
Thank you so much, sir. It was really an outstanding session and very much informative at the same time. Sir, before you leave, I would like to present a very small token of appreciation. Allow me to share my screen.
All right. Thank you so much.
You're most welcome, sir. We'll also mail the certificate to you shortly.
Okay. Thank you. All the best, all of you. Look after yourselves.
Thank you so much, sir. We're really thankful to you for your kind and valuable presence with us, and definitely look forward to have you with us again in such kind of session in future. Yes.
All right. Okay. Take care. I'm happy to help.
Thank you, sir. To all the participants, you can see the taste form and the attendance form has been shared across Google Meet as well as the YouTube streaming meeting link, and it will stay live till 5 p.m. Next, I would now like to invite Professor Dr. Tarun Kumar Ghosh, who is the professor and head of the Department of Computer Science Engineering in Artificial Intelligence and Machine Learning. and also the organizing chair of this FDP RTMML 2022 to give the vote of thanks and conclude the session. Over to you, sir.
Thank you, Vijay. Am I audible to you all?
Yes, yes, sir. Yes.
A very good afternoon. It is an honor for me to get the opportunity to thank you all on behalf of organizing committee of the FDP on research trends and methodologies in machine learning. I would like to express my gratitude to all esteemed speakers of the FDP, Professor Kotagiri from University of Melbourne, Professor Umapada of ISI Kolkata, Professor Arjit Sur, IIT Guwahati, Dr. Sriparna Saha, IIT Patna, and Dr. Aradhana Mallik, IIT Kharagpur, for their valuable knowledge sharing and contribution to make this event a great success. I extend my gratitude to our Chief Patron Dr. Lakshman Chandra Seth, ex-MP Lok Sabha and Chairman HIT, for providing all the facilities and encouragements to organize this program. I'd like to offer our thanks to our principal, Professor Subrata Mondal, and Registrar Dr. Anjan Mishra for encouraging us to organize such program. I'm thankful to Professor T.K. Jana, Dean School of Engineering and Coordinator IQAC, Internal Quality Assurance Cell, HIT, for his precious time and guiding us. I am thankful to the HIT administration in general for providing us with all possible supports towards organizing this program. I'm thankful to all participants for their enthusiastic participation in this FDP. It must be noted that we have received more than 1,100 participant registration. I take this opportunity to thank all the advisory and program committee members for providing their valuable comments towards the quality enhancement of the FDP. I must thank the whole organizing team, especially Professor Subhankar Joardar, Dr. Sumana Kundu, Dr. Sabyasachi Samanta, Professor Abhijit Sarkar, Professor Abhirup Padia, Professor Soumen Ghosh, Professor Shantanu Kole, and Dr. Anupam De for working hard during the past few days to make this FDP successful. Thank you everyone once again for your precious presence over the last 5 days. Over to you, Abhijit.
Thank you so much, sir. Thank you for your kind words. So, as you have mentioned earlier, also the attendance form and the test form has been live, and it will stay live till 5:30 p.m. Around 5:30 or 5:35 p.m. So, requesting all the participants to appear for the test. Based on attendance and this online test submission, we will circulate the participation certificate within next week. Appearing in the online test is mandatory to qualify for the certificate. So, on that note, we are concluding the 5-day long FDP on research trends and methodologies in machine learning, RTMML 2022. Thanks to all participants for your cooperation and patience listening. You have been really a wonderful audience. So, hope to see you all in our next edition of the FDP soon. Till then, happy learning and stay well. Thank you.
Thank you. Bye-bye.
parallelism? You can see. বলছি বন্ধ করে দেবো তো মিটিংটা? হ্যাঁ, আর 5-10 মিনিট থেকে যান। আচ্ছা ঠিক আছে, হ্যাঁ হ্যাঁ ঠিক আছে, ঠিক আছে। এখানে এটা রেখে থেকে কাউকে দিয়ে দাও। মমতা দিল্লি যাচ্ছে না, আপনি হয়ে গেলেন? হ্যাঁ, মমতা দিল্লি যাচ্ছে হয়ে গেলেন? হ্যাঁ, কেন গো? তুমি কথা বলো তো, কাম শুনে যাবে তো, আমরা একটু বাসনে নাও, আমাকে গুরু দাও। আচ্ছা ঠিক আছে দিদি, আমরা গুরু দিয়ে যাবো। আচ্ছা ঠিক আছে। ডিসকাস করতে না কি বলছি, একটু আসবে না, জয়েন করছেন, জয়েন করছেন, করছেন। আমরা তো লিখে আছি, রিপোর্ট কিছু তার অফিসিয়াল কিছু বলে না। কেমিস্ট্রি একজন এখন জয়েন করে 3 লাখ বলেন রিপোর্ট করবে, কি এটা বলো, কেমিস্ট্রি একজন জয়েন করেছে, তাকে ফোন কি দেওয়া হবে, তোমাকে দেওয়া বলবো যে মনিটর কি করে আছে, এটা কি হবে, তার উপরে করতে হবে, এটা বলছে এটা কি হবে, এটা এনএফটি জানে কথা কি ব্যাপার, তোমাদের ক্লাস না আরে নেই বলে আমরা হাত সেমিস্টার দিলো করে লোকটা চেঞ্জ করেছে, কিন্তু এখন করতে অনলাইন করে শুরু করবো, যদিও আছে, যদি তাকে দেওয়া হয় তাহলে কবে জয়েন করতে হবে, পয়লা আগস্ট, যদি সে জয়েন করে, জয়েন করে তার হাতে রুটিন ধরে দেবে, কিন্তু তুলে কোথায় কিন্তু সে তো কি করবে, বসবো, বসে যাচ্ছে তুলে দেবো, বেশি চাপ নেই, একেবারে চাপ নেই। দিল্লিতে গাড়ি লোক কিনে নিয়ে নাম্বার প্লেট করে গেছে না, যে দোকানে এলএক্সআই মডেল কিনেছে, এলএক্সআই কে পুরো চেঞ্জ করে দিয়ে জেডএক্সআই পাস করে দিয়েছে। এর মানে টাচ স্ক্রিন আলাদা করে লাগিয়ে দিয়েছে, কোম্পানি থেকে লাগিয়েছে না, অন্য দোকানে গিয়ে যারা গাড়ির কাজ করায়, আচ্ছা এখানে মারুতি পার্ট, তারা পুরো গাড়ি খুলে দিয়েছে, ভেতরটা সিট ফিট খুলে দিয়েছে, দিয়ে স্টিয়ারিং এর তো নব নেই, ইলেকট্রিক স্টিয়ারিং এর নব নেই, নব লাগিয়ে দিয়েছে, সব ফাটিয়েছে, হ্যাঁ জিনিসগুলো কেটে অন্য সিস্টেমে খুলে দিয়েছে, দিয়ে তারপরে দরজা খুললেই সুন্দর একটা নীল আলো লাগিয়ে দিয়েছে, আর সুইচ টিপে দিলে নীল লাল সবুজ বিভিন্ন কালার হয়ে যাচ্ছে সময় সময়, হ্যান্ড রেস্ট পিছনে যে এখানে লাগিয়ে দিয়েছে একটা কোম্পানি করে উপরে পাশে কি নষ্ট হলে দোকানে যেতে হবে না, ভালো কোম্পানি নাইট্রো ফিচারটা হয়ে গেল, এখানে কি কোন গাড়ি তো আর টাকাই হবে, তুমি লাগাতে পারো, তুমি লাগাতেই পারো, এই মাসে যাই বড় হয়ে যাবে, আমাদের ব্যাংকটা খারাপ সেটা আসলে তুমি চেঞ্জ করতে পারো, আর একবার ফাঁকা করে পাওয়া যায়, হ্যাঁ মোটর পুরো খুলে করতে হয়, হ্যাঁ পুরো খুলে সার্কিট চেঞ্জ করে দেওয়া হবে, বক্স লাগিয়ে দিয়েছে, টুইটার লাগিয়ে দিয়েছে, উপরে সেই আলো লাগিয়ে দিয়েছে, সিট কভার লাগিয়ে দিয়েছে, লেদার সিটটা পুরো পিছনে সিটে হেডরেস্ট নেই, হেডরেস্টটা লাগিয়ে দিয়েছে, পুরো চেঞ্জ করে দিয়েছে, কত করে এটা বলেনি, আমরা হয়তো 1 লাখ টাকা করে দেব, 2 লাখ টাকা করে দেব, কিন্তু নরমাল এলএক্সআই থেকে এলএক্সআই টাকা চেঞ্জ করে দিচ্ছে, অ্যালোই করে দিচ্ছে, সাইডে বাড়ি দিচ্ছে, সাইড বাড়ি একটা ওটা একটা কনফিগারেশন ব্যাপার আছে, এতটা গ্যাপ আছে কিছু হবে না, দাদা ওই গাড়ি হলো প্রত্যেকটাই তো রিসপন্স লাগিয়েছে, তো তোমার তো প্রত্যেকটা ইঞ্জিনের তো ইয়ে সমান, কত কত কিন্তু আলোয় 15 ইঞ্চিরই আলোয় ভুল পাওয়া যাবে, 15 ইঞ্চির আলোয় ভুল পাওয়া যাবে, সবাই ইঞ্চি না, আমি ভাবছি না ওই এটা লাগাবো, ওটা একটা এলএমটা লাগিয়ে সামনে, ওটা তো হুন্ডাই পাওয়া যাবে, সাদা লাগাবো না হলুদ লাগাবো, হলুদ তাহলে কুয়াশা হয়ে গেলে প্রজেক্টে কাজ করবে না, ওই সাথে কাজ করবে না, আমাদের অত কুয়াশা হয় না। কি বলছো, মানে একটু লোককে ডিস্টার্ব করে দেওয়া, ঠিক আছে, শুরুতে লোককে কথা বলতে ডিস্টার্ব করে না, ডিস্টার্ব করতে ডিস্টার্ব একটু সাদা লাইটে ডিস্টার্ব করার জন্য যদি নারায়ণ তো ভালো দেখা ছড়িয়ে যায়। আমি ভাবছি এটা ওদেরটা এখানে লাগিয়ে করা আরে আজকে সে বিয়ে ছিল, চিকেন পকোড়া আর ভেজ রোল ছিল, যদি এতক্ষণ দেরি করে নেন আমি খাওয়ার জন্য আমি কিছু যখন আসবে তারপরে যখন শুনবো এটা তুমি ভাব শিখতে হবে। ম্যাডাম ম্যাডাম ম্যাডাম, হ্যাঁ ম্যাডাম, ম্যাডাম যা থাকে কটায় না কটায় উঠে, ম্যাডাম যা থাকে ও ট্রেনে ঘুম ভেঙেই ব্যাগ থেকে সব বের করে দিয়ে এদের আবার বলুন ব্যাগ কেন রাখছি, ব্যাগ ব্যাগ রাখো ভিতরে ব্যাগ কি বলছি, ভিতরে ব্যাগ কি বলছি, টিচার দেখলে প্রিন্সিপাল খালি দিয়ে যাবে তুমি কালকে আসছো না, কালকে আসার কথা বেরিয়ে যাচ্ছ, এই ছোট দিয়ে তো নাকি ব্যাগ নিয়ে এটা কি করে দেবে, হ্যাঁ তুমি কি বলছো, ঠিক আছে কি বলছো, ঠিক আছে লাইট করবো, দাদা আমি তো দিয়ে যাবো, আমার কি বলছি তাকে বলছি আমার কি লাগিয়ে দিল কিনা। is তাহলে আমাকে মুক্তিগুলি দেওয়ার আগে একটা স্লাইড করে দেবেন কম্পাইল কারা কারা ওই ইনফরমেশন কমপ্লেক্সের শিকার